Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Tangent Planes in 3 Dimensions. As always, please be an active learner as you watch this video. By way of introduction, recall that the important role that tangent lines to a curve played in Calculus 1. In 3 dimensions, the tangent plane plays a similar role. Suppose a surface S, which is shown as the blue surface here, has the equation z equals f of xy, where f has continuous first partial derivatives, and let this point x0, y0, z0, called P, be a point that lies on the blue surface. And let C1 and C2 be the curves obtained by intersecting the vertical planes y equal y0 and x equal x0 with the surface S. Then P lies on both C1 and C2. And if we let T1 and T2 be the tangent lines to the curves C1 and C2 at the point P, then the tangent plane to the surface S at that point P is defined to be the plane shown in brown here that contains both tangent lines T1 and T2. And here is a picture of the geometrical consideration. Now, it turns out that if C is any other curve that lies on the surface S and passes through that point, then its tangent line at P also lies in the same plane. That is a consequence of the continuity assumptions. Therefore, you can think of the tangent plane to S at P as consisting of all possible tangent lines at P to curves that lie in S and pass through P. The tangent plane at P is the plane that most closely approximates the surface S near the point P. And we know that the equation of any plane going through x0, y0, and z0 is represented as A times x minus x0, B times y minus y0, and C times z minus z0 is equal to 0, where A, B, and C are constants. And so dividing all the way through by C, and we letting lowercase a, b minus a over c, and lowercase b, b minus b over c, we can rewrite this equation. We're solving for z minus z0. We get z minus z0 is equal to a times x minus x0 plus b times y minus y0. Now, suppose then we look at the intersection of the plane y equal y0 with this, and this is a tangent line called T1. And so when we do that, y is equal to y0, that term drops out, and we have z minus z0 is equal to a times x minus x0, and this is the equation for the y plane. But this equation right here is the equation of a line with slope a in point slope form. But we know that the slope of that line is the partial of f with respect to x evaluated at x0 and y0. Therefore, a is equal to f sub x, that's the partial of f with respect to x at x0, y0. Similarly, if we intersect the plane x equal x0, we get this, and it follows that b has to also be the partial derivative of f with respect to y, evaluated at x0, y0. So we've proven this theorem. Suppose f has continuous partial derivatives. An equation of the tangent plane to the surface z equals f of xy at the point x naught, y naught, z naught is z minus z naught is equal to The coefficient here is the partial of f with respect to x evaluated at x0, y0 times x minus x0, plus this is the partial with respect to y evaluated at x0, y0 times y minus y0. And if you look at this equation, you can see that it is very similar to the equation of the tangent line in 2 dimensions. It's sort of a dot product version of that. Let's take this out and solve a problem with this. So I'm asking you here to find the tangent plane to this is going to be an elliptic paraboloid at the point 1, 1, 3. You know what to do. Let's see how you did. Okay, so we know that we have to compute f with respect to x, the derivative of f with respect to x, which is going to be 4x. And when we put 1, 1 in there, we get 4. And the other coefficient is going to be the partial with respect to y. And that's going to be 2y. And we put 1, 1 in there, and we get this. So then, and the point is 1, 1, 3, so does z minus 3 is equal to 4 times x minus 1 plus 2 times y minus 1, and we could simplify that and write that as this being the equation of the plane. And indeed, if we take that elliptic paraboloid graphed in 3 dimensions and we start shrinking it closer and closer to the point 1, 1, 3. Now notice here we're going from plus or minus 4, we're going plus or minus 4 in all directions. You can see it's pretty different, but the closer we get, here we go from minus 2 to 2, and here we go just from 1 to 2. We're getting closer and closer, and so you see it is, in fact, aligning. The plane is a very good approximation for what's happening on the surface near the point 1, 1, 3. Similarly, if we're looking at the contour plots, zooming in on 1, 1 on a contour map of this, we get this, this, and this. You see it's becoming closer and closer to being parallel lines, which is exactly what you would get if you were talking about a plane. Let's do another problem. Find the tangent plane to the paraboloid z equals x squared plus y squared at the point 1, 2, 5. You know what to do. Let's see how you did. So we know from our theorem that the equation of the plane is going to be z minus the z coordinate of the point, which is f of 1, 2, which we know is 5. And that's equal to the partial with respect to x evaluated at 1, 2 times x minus 1, plus the partial with respect to y at 1, 2 times y minus 2. The partial with respect to x is going to be 2x. The partial with respect to y is going to be 2y. So when I put in this point, I get 2. And substituting here, I get 4. And this, of course, was 5. So this is z minus 5 is equal to 2 times x minus 1 plus 4 times y minus 2. And solving this, I get z is equal to 2x plus 4y minus 5. Now we do have many applications of this, so let's review when we might end up using this. And again, recall that the tangent plane to a surface at a point is found using partial derivatives. The equation for the plane can then be used to calculate linear approximations of a function near the point. So, some applications. Automobile designers often use headlight reflectors in the shape of a paraboloid, which can be approximated using tangent planes found at many points on the surface. Consider golf balls. Irregular surfaces often require complicated calculations. This is very irregular. You can see all these indentations. A manufacturer of golf balls must analyze the ball's surface. Tangent plane equations can approximate various points on the ball using much fewer calculations than an exact equation for the surface. The last example is meteorologists consider barometric pressure throughout a forecast area. The pressure at ground level can be modeled by a function of two variables, longitude and longitude. The equation of the tangent line can be used to approximate the pressure at points in the forecast area between these data points. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.